Today, I'm going to talk about one of our paper. It's called the comparative dynamics in a dynamic oligopoly model of capital accumulation. So this is a joint work with Professor Schraven from the University of Nottingham, and also the Professor Bruno from the Italian people. Okay. Now, first of all, ever since Samuelson 1947, well, at least the economists start to realize that comparative statics has become a cornerstone in the analysis of the economics model. I will say at least like 90% of the applied econ papers, one way or another, are working on this sort of like comparative statics. Maybe was some paper in the management sense as well. So it's always important to develop some approach to get comparative statics results. Okay, but in a dynamic setting, its counterpart is somehow called comparative dynamics. Well, the definition is similar, which describes the direction of change in the optimal path of decision variables as a result of changes in exogenous variables. So this is very common in dynamic economics models, also in differential games. Okay. So, however, well, the study of the comparative dynamics in differential games has mostly focused on steady state or models with specific functional form, or mostly the linear quadratic model. Okay, we just name a few, like the benchmark from the McGill. Caputo and I had some papers in the 2011. Also, George had a bunch of paper working on this direction as well. Okay, now our paper is trying to propose a new method to trace the path of comparative dynamics in a general class of differential games. So we are hoping that we can pin down the sign of comparative statics at each instant of the game. Our method is not new. We actually based on the Oniki's classical paper. It's so-called the variation approach back to the 1973. So, and also we demonstrate our method in the well-known well-known capital accumulation differential game. So that's why so that's how we put together the title of the paper. Okay, now what are some related works right here? So our paper, first of all, enhance the understanding of the base properties of the capital accumulation games. Well, this is I would say a workhorse model in differential games. So lots of work has been done in this area. Like the previous study, like focused on the existence and the stability of the equilibrium, the compact properties, and the derivation of open loop and the feedback Nash equilibrium, and also some like the intertemporal strategic substitutability or complementarity. Also, we have done some work on this area, working on the comparative dynamics in a steady state. Also, the cumulatively effect of the change. Okay, so this is one possible relate. Also, we argue that our paper also provides some contribution to the methodology of the comparative dynamics in this in differential game theory. Like we said, most applications are either use this some specific functional forms or in the neighborhood of the steady state. Also, we have done some work on the for the feedback equilibrium for the baseline of the game. Also, we can actually we have also some works on the cumulative effect of the.
What is the baseline of the game?
Well, basically, it's just the initial time, because if you think about the feedback, you get the Hamiltonian Jacobian is the baseline. Okay. Also, our paper also work. So there's a typo here. Also, relates to a small but fast-growing literature that employs the so-called variational differential equation proposed by Oniki, but most of this paper in the optimal control setting. So we believe that our paper is the first to apply this method to the differential games. Okay, so this is basically some ideas. Now we can go to the model. So the model is classic and quite straightforward. Okay, so the K is a capital, and so the W is the maintenance cost for holding these capitals. I is the investment rate, and the Q is the price of the investment. The C is a cost function that that's saying that if you add in some investment to the firm, you're gonna incur some cost. Okay. Then we have some the dynamic of the capital is based on the investment rate minus some depreciation rates. Okay. Now here we do not impose any functional form on pi and the C, also for the F. So in some sense, our model is quite general because we do not impose any functional form. So given that we cannot get any closed form, the closed form solution, also we cannot solve it numerically. Okay, so we have to establish some propositions here. Okay, so this is the basic idea, but we do impose some structure. First, we as usual we assume that pi is concave in its own capital, and also the cost function is a common convex function, which is pretty standard. Also, we assume that the production function of the investment is either constant return to scale or decreasing return to scale. Okay, so this is our basic assumptions right here. Now our paper focused on open loop information structure, so we only consider the open loop Nash equilibrium. Well, in principle, our method can be applied to the feedback, but the math is going to be, it's going to be math. So maybe in the future we can deal with the feedback case. Okay. Now, given all this, then then we have some standard method to solve this question. Okay. Now we define the current or the current value Hamiltonian for each firm, which is given this. Then we can get the first order conditions, which is very it's a classic one. Okay. So then in our paper we only consider the symmetric case. Okay. Again, in principle, the method can be applied to the asymmetric case, but as a benchmark or as a starting point, we believe that investigating in the symmetric case can serve as some sort of like the benchmark to compare in the future. And also the symmetric case, the symmetric really helps to reduce the mass quite a bit. So because of the symmetric case, that we can also reduce the notational form. We can simply just write the lambda I and k. Okay, so it's easy. Now after that, by some math derivation, which is pretty standard, we will get the following system of differential equations, which is that came from equation 4 and 6. Okay, so this is also pretty standard. Then in principle, we can actually solve these two ODEs to get the solutions, lambda and the k, right? At least in principle, okay? Then from equation 3, from this first order condition, we can get the open Nash equilibrium I, which is depending on the lambda and the parameters. Okay, so this is the idea, right? So if you have if we have some functional forms on pi and f, like so we can end up with some closed form solutions. Okay. Now our goal is to get some comparative dynamics. So which means that we need to differentiate, we need to get some, so we need to differentiate our solutions with respect to the parameters. Okay, now what we're going to do is that we substitute these solutions back to equation 7 and 8 and differentiate with some parameters and differentiate with respect to some parameters of interest. Okay, that's what we do. So let's say now we have some interesting in investigating the change of the price of Q, right? So the price of Q mass or the price of Q maximum Q. Then it will give us this kind of a system of ODEs. Okay, so Oniki call this as a variational differential equations. Okay, so this is nothing fancy, just differentiate this 7, 8 with respect to the Q, and you can end up with this one. Okay.
So that's the double derivative, right? The notation, this is d2 by d lambda, dq
With-
d dt, right? This is the
dq
double derivative.
dt, yes, with respect to
Q and d.
t, yes, yes,
Okay.
yes. Because this is the dot, so it's a Q here.
Yeah.
And so if we can solve this equation, which actually give us the trajectory of this vector, right? The lambda q and the kq. So this is actually is the comparative dynamics we want, right? So it describes the changes at each instant of time, right? So now once we have this, we can actually substitute this back to this equation, then we can get the comparative dynamics for the imaginary rate. Okay, so this is a general idea of how we get this. Okay, now well the rest is that how do we pin down this equations? Okay, now well the thing that we actually don't care about the solution of this lambda q and the kq. We only care about the sign of the terms. We only want to determine it's either positive or negative. Okay, so that's the goal. Okay, now in order to examine this one, we need to look at this matrix. Okay, so we call this is the Jacobian matrix in equation 9 is given by this, and based on our assumption, we can easily to show that these three terms have a positive, and negative. But this term we don't know the sign of this term yet. So in order to get some nice results, we need to impose another assumption on the sign of this term. So we assume this summation is always less than 0, which
Well, what is the meaning of the summation?
well in a minute. Okay, in a minute. So if we assume this one, then it basically follows that this the Jacobian matrix. Okay, now this summation, it basically says that a firm's own capital second order effects must outweigh its cross second effect, which is quite common in economics setting. Like so, if you recall the profit maximization model, the second order own effect must outweigh the cross second effect. So that gives you the maximum case. Okay. Also, this case will typically sometimes in most of the time I would say it's implicitly assumed in the literature. Like if you write down a linear quadratic model, this assumption automatically holds in most of the case. Okay, so so this is not this is not a very quite uncommon assumption. So we fine with this. Okay. Also, we can actually identify two sufficient conditions to make this assumption hold. One sufficient condition for this assumption to hold is so-called the instantaneous gross payoff substitutability, which defined in Professor Van Long's his survey book. Well, it basically said this second order effect is always less than 0. Then, given this function is concave in its own capital, then we can directly get our assumption. Also, another sufficient condition is the so-called the Hadamard diagonal dominance, defined in Dr. and Takashi's paper. I believe it's a joint paper. What it basically is a mathematical term for saying that the own second effect must outweigh the cross second effect. Okay, so we have these two sufficient conditions to hold that. Now, given all this, we can actually present our main results. Okay, so the impact of an increase in Q is given by the following. Now, if the price of investment goes up, then we can prove that at each instant of time, the lambda Q increase. Okay, and also the K is decreased at each point of time. Furthermore, we can actually get more results on lambda Q. Well, the lambda Q is not just greater than 0. It's in most of time it lies between 0 and 1, or at least for the beginning of the game and the end of the game. Okay, so in the middle of the game, well, the lambda Q may go beyond this area, but it don't have to. Okay, it can stay in this area for the whole time. Also, we can show that if this holds, then we can show that when Q increase, the investment rate goes down. So, which is the typical the law of demand, right? So when the price goes up, then the demand goes down. Now, unfortunately, we cannot establish this claim for the whole horizon. We can only prove that this law of demand must hold when the game approach to the end. But this is not to say that this term must be violated in the beginning or in the middle of the game. Well, it only said that we cannot establish this law of demand at this level of generality. Just think of the utility maximization model, right? We actually cannot prove that the law of demand at that model, because it's possible there exists some so-called the given good, right? But in most of the cases, the given good is not exist, right? And also it's not an easy task to find a given good in reality as well. So this is a similar result here. We can only make sure that the law of demand must hold when the game approach to end. Okay. The proof of this proposition is not very difficult. We can actually demonstrate this proposition use some geometric tricks. Okay, and also we can prove it by the pure algebra as well. Okay, now given this equations, we can actually translate this equation into this diagrams. Okay, now the x is kq and the y axis is the lambda q. Okay, now at each arrow here is indicates that if the system is just reach this point, what he gonna move in the next time? Okay, so let's say if the system reach at this point, okay, now he can well, this arrow dictates that it must go that way. And then how do we show that? Now, suppose the system is sitting right here, then KQ is equal to 0, and lambda Q is positive. Okay. Now we can use this equation to show that the lambda Q dot equal to R plus delta times lambda Q, because KQ is 0, so then this term vanishes. Then we can make sure that lambda Q dot is greater than 0, which means lambda Q must increase. Okay, so at this point, lambda Q must increase. So it either goes this way or goes that way, right? Then similarly, we can show that at this point KQ dot is negative, which means that at this point KQ is decreasing. So if the system reach this point, or this direction is the only possible way he can move. Okay, now the rest arrow was similarly be determined. And also in this point, basically this that the systems can go anywhere. We cannot pin down the sign of lambda Q dot and the KQ dot. Okay, and also the boundary condition here give us some sense of the starting point and the end point. Now, because the KQ so at the beginning of the game, KQ equal to 0. So which means the game must start at the vertical axis, and also at the end of the game, lambda QT equal to 0, which means that the game must converge to the KQ axis, right? So well, by this restrictions, then there is some possibility that the trajectory can looks like. So this is one possibility here, right? Also, we can see that if the system starts with here, then it moves to this area and it continues to decrease, and it never gets back to the here. So we can rule out this possibility. And also, if the system starts from here, then it moves to this area and it decreases all the time, and it never comes back. So the system has to start from this area and always stays in the second quadrant. So this is a possible trajectory, and also maybe something like this. Okay, also something maybe like this one. This is the not a unique solution, but it's just some possibility here. Okay, now given this, we can see that the whole trajectory stays in this area, which means that the lambda Q is always positive, and the KQ is always negative, right? So that actually gave us equation 12 and 13, and the rest of was can be indirectly get from this equation. Okay.
Why is coming this lambda Q equal 1?
This is because we have sorry. This is from math, because we might have some problem right here. F prime So if this is not if it's equal to 1, then everything is equal to 0. Well, this happens in some so this come out from some math derivation. So there's no particular reason to expect that. Okay, now so basically we show that the higher price will lead to higher cost variable and the lower level of capital over the whole planning horizon. Our this results basically generalized, which Renaud in his IER paper took together. So we believe and he did actually in a linear quadratic model. So we extend his results in some sense. Okay, we also showed that the law of demand only had to hold over close to the terminal time. But like I said, this not imply that the law of demand must be violated before that. We just say we cannot prove this at this level of generality, right? So given this, actually, two questions immediately follows. One is that so can we get some extra assumption to make sure the law of demand will hold for the whole horizon, right? So this is a one possible question. Well, the second type of question is that so can you give us a example to show that the law of demand always violate? Okay. Fortunately, we can answer the first question, but unfortunately, we cannot provide any examples to show that this law of demand is violated. So that's what we got in some next slides. We can actually come up with two cases. Case one, if we assume that the technology is constant return to scale, which means that Fi equal to I, which is commonly employed in the literature, then we can show that the law of demand must hold both at the beginning of the game and the end of the game. So which gives you more results. Okay, so for this type of functional form was commonly assumed in the literature. Okay, well, next, if we assume that this summation term is constant, then we can prove that the law of demand holds for the whole horizon. Okay, now the basic idea here that if this is constant, then the crossing point like this can be ruled out. We can no longer get this kind of things, which means that the trajectory must stay between 0 and 1. Then this type of irregularity cannot happen. Okay. So well, if this is constant, then it follows that the class linear quadratic game automatically satisfy these conditions because it's a quadratic. So this the second order must be a constant, right? So which means that if you write down a linear quadratic model, it actually gives you a very nice proposition, like the law of demand must hold. But be careful because this kind of proposition is conditional on the linear quadratic form. You may not be extend this proposition too much, right? Because if you move away from the linear quadratic, this type of things may not be established. Okay, so that's the basic idea I have. Also, now, well, the rest of the proposition is routine, right? So we actually repeat the same procedure for other parameters. But I still like to say something about the proposition 2. Okay. Well, the proposition 2, we examine the parameter of the K naught, which is the initial capital level. Okay. So the impact of an increase in K naught is given by the following. If the K naught goes up, then the capital then the level of capital increase all the time. The lambda decrease all the time, and the investment rate decrease at each point. Okay, so this is a very nice result. Also, it actually well, the proof is very easy. For K0, well, the trajectory looks like this one. Okay, I'm not going to do this. Well, actually, well, the proposition 1 actually gave us an unexpected result, which we have no clue when we start this project. Well, basically, it gave us to help us to establish some sharper envelope results. According to Kabuta and I actually have done some envelope works a while ago. Now, according to our work, if you derive this equation, we can see that the costate variable is not the shadow value of the initial capital, right? So the lambda is not equal to the marginal value of the capital. We have this extra term here, and usually it's not degenerated. Okay. However, it remains unclear whether the lambda overestimate or underestimate the shadow value of the state. Well, you can see that at this level of generality, we don't know whether this term is positive or negative, right? Well, in our 2012 paper, we actually compare these two terms in a linear quadratic model by some numerical simulation stuff. We show that the lambda is actually underestimate the shadow value. So, but that is just examples. Okay.
What is the intuition behind it? Well, why it's like that?
I don't know.
There is no clue.
We just don't know why is that. Well, this is actually also makes sense because in optimal in maximization problems, we always said that the lambda captures the shadow value of the constraint, right? But in a game setting, this is not true because this costate variable alone can only capture the non-strategic part of the shadow value, because if the initial value changes, it may affect the other players' behavior, which may indirectly impact the of my values. So in a game setting, this strategic effect is cannot be degenerated. So we have this values term here. So in general, we cannot say the costate variable is the shadow value of the state, at least in the open loop Nash equilibrium. Okay, so this is the basic result, and we actually
So here you are saying that you don't know how to estimate this IK naught, like this whole term. You don't know how to estimate this whole summation integral.
Yes,
right.
Yes.
So, but you mentioned that you can do this comparative dynamics. It's like you cannot compute it analytically, or you cannot compute it at all.
Well, at this level of generality, we cannot compute it at all.
And numerically as well? Like I'm saying that numerically, can you compute? Because now
numerically, of course, you can.
Okay.
if you assume like the linear model, of course, you can get this one. Actually, that's what we did in our 2012 paper. We actually work on this linear model, and we show that this is so this term is positive.
In fact, you can do it for more general models numerically, right? You have to just compute these differentials, right?
Yes. We can do that, but here we can actually prove that this term is positive.
Okay.
All the time. So now look at this term, right? So this is this is nothing but the comparative dynamics. We just so we just get, right? Remember that here. The ik0 is less than 0 all the time. So this term is nothing but the comparative dynamics. And also, if we know something about this lambda, then we can actually to determine the sign of this term. So we can actually pin down the sign of this term from one of the necessary conditions. Okay, we can show that if this assumption satisfied, then this term is always less than 0. Okay, and we believe that this is not an uncommon assumption, because it basically said that if other players' capital goes up, it always hurts me, right? Because my competitors have a much larger capital, which is always bad news for me, right? So this is the basic idea behind this. So if this is true, then we can actually to establish that the lambda is always less than the shadow value of the capital. Okay, so well, actually this is a totally unexpected result at the beginning. When we get to this point, we see that we can actually to establish this claim. So
what is VP?
V is the sorry, I haven't mentioned that. VP is the optimal value of the 4 players. So which means that if the initial capital goes up, what's the value for players? So basically, it's the marginal value of the constraint. Right. So this is VP. I'm not sure if this answers the question.
Is it the value function in dynamic programming sense?
Yes.
So you are getting it once you apply the equilibrium solution.
Yes. Of course. Yes.
So at equilibrium, what you are getting is this result that is a bit surprising. Yes.
Everything here is along the open-loop Nash equilibrium. It's not it's not called off the equilibrium, right? So everything is along the equilibrium. Okay, so that's what we have. Basically, now the rest of the proposition is just repeating works. Okay, so I probably just skip out of this. We actually do this comparative dynamics for all the parameters, which is PBS. Okay, now here are some conclusions. Okay. We characterize the comparative dynamics of symmetric open-loop Nash equilibria for the capital accumulation game, and it's a quite general one. And also we argue that our results help us to produce some sort of like sharper results. Okay. Well, of course there are some possible extensions of our works. Well, first of all, maybe we can work on even more general models. Okay, here we deal with some general models, but still we have some mathematical structures on the models. Maybe in the future we can start from the models with just F and G. Okay, so there's no other structures, just the F and G, right? So this is one. So this is one possibility. Also, we can work on the feedback information structure. So I know that most of the economists, prefer this type of concept, right? So, well, in principle, we can apply our approach to the feedback, but as we all know, because there's some extra term in the first order condition, that's gonna greatly complicate the math. Okay. Also, we can do this type of work in more applications, like the famous sticky price model in the econometric paper, and also some like the resource extraction paper, so on and so forth. Okay, I think that's the presentation I will give. So you can. Thank you.